Hey, chemistry. We're going to talk about how the intermolecular forces affects the melting and boiling points of substances. We're going to be able to rank the substances by their boiling points based on the type of intermolecular forces that they have. All right, so let's take a look at our states of matter. We're going to focus on the states of matter of substances at room temperature and relate them to their intermolecular forces. So substances that are a solid at room temperature have very strong intermolecular forces, which cause them to have a rigid structure in which the individual atoms are vibrating but unable to break free of that overall rigid structure. Liquids have intermolecular forces that are sort of at a medium level. These particles have enough interaction that they're able to stay together in the same volume. They're not able to go wherever they want, but they're not enough to escape wherever they want to go. So they are stuck basically circling around each other without being able to freely escape. Gases have the weakest intermolecular forces at room temperature, so that indicates that these have enough kinetic energy they can escape these weak intermolecular forces and escape as a gas. All right, so I posted a video called Phase Change Simulations that are showing you what's happening at the molecular level as these atoms go from solid to liquid to gas. But let's look a little more deeply at boiling point. We'll use boiling point as something that allows us to compare all the different substances. So boiling occurs when the molecules of that substance have enough kinetic energy that they can overcome the intermolecular forces that are holding them together. When water is boiling, that means the water molecules have enough kinetic energy that they can overcome that hydrogen bonding, that dipole-dipole interaction, and escape as a gas. And the bubbles that you see when it's boiling are bubbles of water vapor, of water as a gas. The stronger the boiling, the intermolecular forces, the higher the boiling point. So you can actually rank them by determining what type of intermolecular forces do they have, and therefore where should they rank relative to other substances. Substances that have extremely low boiling points are often nonpolar compounds. So when you think about all of the gases that exist at room temperature, we're talking about oxygen and nitrogen and carbon dioxide and all of those gases, that's because they're nonpolar. So they have very weak intermolecular attraction. So in order to hold them into the liquid phase, we're going to have to cool them way, way down. All right, so I'd like you to take a look at these three molecules. They're all diatomic molecules, and what I want you to do is rank them by their boiling points. So I want you to think about that the larger the molecule, the greater the dispersion forces, and that would result in higher boiling points. So take a moment, pause the video if you need to, and think about what do you think the boiling points of these substances would look like. Okay, so chlorine is a greenish gas that has a boiling point of negative 34 degrees Celsius. The other way to look at it is if you wanted to condense it into a liquid, you're going to have to cool it way down to negative 34 degrees Celsius. That's colder than most freezers can get to. Bromine is a liquid at room temperature that can turn into a gas at 58 degrees Celsius. So that's its boiling point. It can actually start vaporizing at temperatures cooler than that, just like water can evaporate at cooler than its boiling point. But 58 is its boiling point. So it's this brown liquid that turns into this brown gas. And iodine is a solid at room temperature that will sublimate, that will turn into a gas at 184 degrees Celsius. So you'll notice that the pattern here is that all three of these are diatomic. All three of these are in the same family, the halogen family. So what's changing between chlorine and bromine and iodine? And what's changing is the atom size. As you go down the periodic table, we're adding a shell and they're getting bigger. And as they get bigger, they have greater dispersion forces, and then that's going to result in higher boiling points. Okay, so let's take a look at some other examples. So here's methane, and all of these are going to be chains of carbons. So these are all nonpolar molecules that are chains of carbons with hydrogens attached. So methane contains 1 carbon, and it has a boiling point of negative 258 degrees Celsius. That's incredibly cold. In fact, even under pressure, it's hard to turn methane into a liquid, which is why when you have natural gas delivered to your home, if you have natural gas, which is methane, it's delivered as a gas. It's not delivered as a liquid. Propane, on the other hand, which is a chain of 3 carbons, has a boiling point of negative 42 Celsius, so much warmer. Still very, very cold, but it has enough dispersion forces that under about 5 atmospheres of pressure in a steel container, we can liquefy it. So if you take a propane, like a Coleman propane tank you can buy at the store, and shake it, you'll hear that liquid that's inside because it's under pressure. Those propane molecules have been forced together under pressure, and then they stick due to intermolecular forces, these dispersion forces. Butane, which is lighter fluid, has 4 carbons, and again, its temperature goes up to -1. Hexane has 6 carbons, and its boiling point is 68 degrees Celsius. It's a liquid at room temperature. If you're wondering what is room temperature in Celsius, it's about 20 to 25 Celsius, so this is well above that. So hexane is a liquid at room temperature. Mineral oil, which has 18 carbons, has a boiling point of 350 degrees Celsius. So that is clearly up there. You're going to have to basically light it on fire to get those kind of temperatures. And so mineral oil is, as you are aware, a liquid at room temperature. Petroleum jelly, 360. It has 22 carbons. And finally, paraffin, also known as candle wax, has 25 carbons and has a boiling point of 370. If you want to know what paraffin is at room temperature, well, it's a solid. It's what a candle is like. Now, what happens when you light a candle? First, as it heats up, it melts, and then it vaporizes. And it's actually the vapor, the gaseous form of paraffin, that creates the flame that you see on a candle. All right, in our next video, we're going to be looking at ranking substances a little bit further and talk about something really cool called the Leidenfrost effect.